Welcome back from break. Now we are going to continue to move on to section 7.2, where we're going to look at the relationship between molar mass and between molar mass and moles, and we're going to learn how to do calculations, okay? So you can see in the image that we have here, we have several beakers that have 1 mole quantities of the particular compounds that we have. As you can see in the first one, we have just sulfur. In the next one, we have iron. In the next one, we have sodium chloride. Then we have potassium dichromate. And lastly, that is sucrose. And we're going to learn about sugars in chapter 13, but I just wanted to at least introduce it. We can see that each of these beakers, even though they have 1 mole quantities, it is hard just by looking at the chemical formula saying, oh, okay, so I can eyeball what 1 mole is. One of the ways in which we are going to count these moles is by actually measuring them in grams, because in the laboratory we have top loading balances that are able to measure the grams of a compound that you're interested in. So if you need mole quantities of a particular element or compound, it is hard to just visually to say like, oh, this is about 1 mole. No, we need to learn how to do the conversions between 1 mole and grams so we can measure correctly how many grams are in the particular molar quantity that we need of a particular element or compound, depending on the reaction that we're trying to do. So how do we do that? We're going to learn how to do molar mass conversion factors. We know already that a mole of a particular atom is going to equal Avogadro's number of the atoms of that element. But understand that that is also related to the amount in grams of that element. And you can see here that if we are trying to get 1 mole of carbon, that will be 12.01 grams of that carbon atom. How is it that we get that number specifically for 1 mole of carbon? This number that you see here, that 12.01, actually refers to the atomic mass of the element. And as we learned previously, the atomic mass is going to be those numbers that are below, in most periodic tables, the symbol of the element. So when we are doing molar mass conversions, what we're doing overall is relating the grams of a compound or an element to the moles of that compound or element, okay? So the first thing that we are going to learn is how to calculate molar mass. And in order to do this, this is why it's important that we know how to name compounds. When it comes to this in exams, understand that the name of the compound is going to be given in words. So from the words given, you need to derive the correct chemical formula, okay? So let's first determine the chemical formulas for the following compounds, starting with magnesium chloride. Let's put it in the chat. What is the chemical formula for magnesium chloride? Excellent. MgCl2. What about potassium permanganate? What is the chemical formula for potassium permanganate? There's 18 of you out there. Potassium permanganate. Excellent. KMnO4. And lastly, zinc nitride. Chemical formula for zinc nitride. Excellent. ZN3N2. So once we have the correct chemical formula for a particular element, what we need to do is list the atom types, okay, that we have there. So for magnesium chloride, we have 1 magnesium and 2 chlorines. For potassium permanganate, we have 1 potassium, 1 manganese, and we have 4 oxygens. For zinc nitride, we have 3 zincs and we have 2 nitrogens. Put a 1 in the chat if so far is making sense, the work that we are proceeding to do. Excellent. So when we're trying to calculate the atomic mass, all what we're trying to do, okay, is take this value for the number of atoms and multiply it by the atomic mass of that element. So let me just do the example for magnesium. So I'm going to say magnesium, I have 1 of them. Chlorine, I have 2 of them, okay? If I utilize the values in the periodic table, actually that's gonna be very little space. Let me just do it below. So if I have magnesium, there's 1 of them. Chlorine, there's 2 of them, okay? Magnesium has a mass of 24.3050 grams per mole. So those are the units coming out of the periodic table. If you don't write grams per mole, then you can write AMU, which is atomic mass unit. Okay. Then when we go to chlorine, is 35.453 grams per mole. Okay. For those students that are like, Dr. Luz, where are you getting those numbers from? The periodic table. Okay. So 1 times the 24.3050 is going to be 24.3050 grams per mole. For chlorine, 35.453 times 2 gives me a value of 70.906 grams per mole. And then I'm going to add these 2 numbers, okay? That's 24.3050, okay? So I get a value of 95.211 grams per mole, okay? So when it comes to atomic mass, okay, understand that it's going to be the same value numerically as molar mass. It's just that the units are going to be different. When we have atomic mass, then we put the unit of AMU, okay, atomic mass unit. That's going to be for atomic mass. When we have molar mass, we're going to put the units of grams per mole. Understand that you must read the instructions. Many times, specifically when you guys do the lab that has to do with all of this, it says that you need to round to 2 decimal places. So that's what I'm going to do right here. So if I take 95.211 and I round it to 2 decimal places, what's going to be the value? Excellent. This is 95.21 AMU. If we're talking about atomic mass, or 95.21 grams per mole if we're talking about molar mass, okay? And that's how we calculate the molar mass for any compound that is given to us, okay? At this time, I'm going to give you guys a couple of minutes to calculate the molar mass for at least potassium permanganate. Let's do together potassium permanganate. So I'll give you guys 2 minutes to calculate the molar mass of potassium permanganate. I'm going to start writing the work, but you guys can continue working on it. Excellent. I start seeing the answers in the chat. So when it comes to this, if we round it to 2 decimal places, and again, make sure that you read the instructions for whenever you have the lab, you get 158.03, and then the digits after 3 is 3945. So that's why we leave it at the 0.03. And this is an AMU versus grams per mole, okay? And that's how we calculate the molar mass for a given compound. Any questions on how to calculate molar mass for a compound? Excellent. So now that we know how to calculate molar mass, we're going to use it in calculations for conversions between grams and moles. So as you can see here, we are going to, in this particular problem that states a box of table salt, in other words, NaCl, contains 737 grams of NaCl. How many moles of NaCl do we have in that box or are in the box? So when we are trying to convert from moles to mass in grams, our conversion factor is going to be molar mass. So again, here, this is just an illustration of the flow chart that I have in the in-class worksheet. For some students that need a visual representation of the actual conversions, that's why I included on the slides, but understand that they're also in the in-class worksheet. So in this case, we're talking about a compound, and we are given grams of the compound, and we need moles of a compound. So when we are given grams of a compound and we need to find moles of a compound, what we're going to do is divide by the molar mass. If the opposite was asked of us, meaning that we were given moles, but we needed grams, then we need to multiply by the molar mass. And it goes the same way. If we are given grams of an element and we need to find moles of an element, we're going to divide by the molar mass. And if we're giving moles of an element, but we need to find grams of an element, then we multiply by molar mass, okay? So in this case, for the question that we have, we're going in this direction. So because our conversion factor is not here, we need to generate it, okay? So the first thing that we're going to do here is that we are going to determine, so we are already on step 3. We already talked about what is given and what is needed. The plan is to convert from grams to moles. We need to go to a step 3, which is going to be determining the molar mass. To determine the molar mass of NaCl, we know that we have 1 sodium, we have 1 chlorine. We're going to multiply that by their respective molar masses. So for sodium is 22.989769 grams per mole. For chlorine is 35.453 grams per mole. So when we add those two values, the molar mass (22.989769 más 35.453) is 58.442769 grams per mole. And then we're going to write the grams of the sodium chloride given, 737 grams of NaCl. We're going to divide by that molar mass, 58.442769 grams per mole are in 1 mole of sodium chloride. The units of grams per mole cancel. And then our answer for moles of NaCl, do it at home. Let's see what we get if we get the same number. Excellent. I got the same number. And thank you for putting the correct number of sig figs. It's 12.6 moles of sodium chloride in that amount of sodium chloride. Okay. This calculation is very important whenever we're doing reactions, as we're going to see later in this chapter, because when we have chemical reactions, even though the reaction will tell us molar amounts of what we need of a particular molecule, but we need to measure in the top loading balance or analytical balance, depending on what you're working with, of the components of your chemical reaction. So that's why this is a very important conversion.
Professor, I have a question.
Yeah, go ahead, Alexa.
After you find the molar mass, I know according to the amount of sig figs, is it okay if you account for the sig figs after you find the molar mass, or do you want us to put that full amount in the next calculation and then wait to round to the amount of sig figs at the end?
That's a great question. So when it comes to these problems, what I prefer is that students just round to the correct number of sig figs as their final answer. The reason why when I first introduced these calculations to you guys, I used to talk about the calculation display is because I want to make sure that since we have a diverse population of students, meaning some students that have taken chemistry, some students that have not taken chemistry, I need to make sure that everybody understands the process. But by now, you guys understand that whenever you're given digits, especially in the calculations for these problems, depending on the number of sig figs that are given to you in the problem, please round your final answer to the correct number of sig figs as a final answer. So you don't have to include the calculator display for any of this.
Thank you.
No problem. And when it comes to molar mass, I understand that maybe students are utilizing or they look at the textbook, the front of the textbook, or other resources for calculation of molar mass. Understand that when I generate these questions and I have the answer key for them, I utilize the periodic table that I provided to you guys as the reference list for exams. So I will encourage you to use that one, because if you don't find the answer that you come up with utilizing your resources, understand that it is because of the discrepancy of the periodic table that I'm expecting that you guys are using versus whatever other research you will be using. So please utilize the periodic table that is given on Canvas, because that is the one that I utilize to generate these answers. So with that, let's do some practice problems, okay? I'm going to give you guys, let's see, there's only 3 problems. I'm going to give you 4 minutes, okay, to do these conversions. Again, we are converting between either moles of element or compound to grams of element or compound, okay? Now, I want to make you aware of problem 2 and problem 3, which is a common mistake that students make. I mentioned to you guys that there's a certain set of elements that are diatomic. Later, we're going to learn how some of these have a specific state of matter. Understand that whenever we have chlorine gas, this refers to Cl2. Or the other way that it is worded is molecular chlorine. In your head, click that is going to be Cl2. Similarly, oxygen gas. Oxygen gas is O2. Molecular oxygen is also another word to talk about it. So whenever you see the word molecular in front of an element that is diatomic, go immediately in your head to the diatomic molecule, okay? So I just want to specify that because it makes a difference whenever you're doing molar mass of Cl by itself versus Cl as a diatomic in your calculation. So understand that, again, chlorine gas or oxygen gas refer to the diatomic, or if the word molecular is in front of an element that is diatomic, then we're referring to them with a subscript of 2. So again, I'm going to give you guys 4 minutes and we will go over these answers. let's get started. In the first one, it reads, how much do 8.13 moles of neon weigh in grams? So our conversion is from moles of neon to grams of neon. So we're going to write what is given, 8.13 moles of neon in 1 mole of neon, because remember that we want to cancel the units of mole. There's going to be specifically 20.1797 grams of neon. So when we make this conversion, what number did you guys get? Excellent job. 164 grams of neon. In the next one, we have 0.345 moles of Cl2 in 1 mole of Cl2 there are 70.906 grams of Cl2. The units of mole of Cl2 cancel. And then we have grams of Cl2. So what did you guys get for that one? Excellent. That's what I got also. Lastly, we have 1.11 moles of O2 in 1 mole of O2. There's 31.9988 grams of O2. What did you guys get? Excellent. I got that also. $35.5 grams of O2. Any questions doing transitions between grams to moles, like we saw in the first example that I did, or like these, which are moles to grams? Excellent. Another transition that we can learn how to do, taking into account molar mass and incorporating the concept of formula subscripts, is that we can calculate specifically the mass of an element given the mass of a compound. So again, in this problem, this is what is given, and this is what is needed. When we have that conversion, then there are 3 conversion factors that are utilized. The first one is the molar mass of the compound to discover how many moles of the compound we need. The second conversion factor is going to be the formula subscripts, which the formula subscript is going to tell us the relationship between the moles of the compound and the moles of the element. Lastly, we have the molar mass of the element, and that last conversion takes us to the grams of the element. Okay, put a 1 in the chat if you like cheese. Put a 2 in the chat if you have eaten vegan cheese, because that's what I have to do, because I'm allergic to milk. in any milk product. There you go. People have tried it. Awesome. It's for some things, it tastes very similar. Like by now I'm used to it. I do miss cheese. When I moved to mainland US and I started my studies here, I used to live in Wisconsin. This dairy allergy is something that is recent to me. So I was like, oh my God, after all these years, the inflammation that I live with was because of the dairy. I didn't even know. It was interesting. But again, vegan cheese, very delicious. Now, in this problem, it says that 1 cup of cheddar cheese contains 4.05 grams of table salt, okay? Now, we're trying to determine that even though we have those grams of that compound, sodium chloride, in other words, table salt, we're interested specifically in the grams of sodium. Sodium is one of those ions that we also have to keep an eye on, just because if you have a high sodium diet, it can actually cause, or it has been correlated with certain diseases, blood pressure, heart disease and all that kind of stuff. So at times we have to make sure that we don't have a diet that is high in sodium. But in this problem, we're going to see how utilizing the different conversion factors that we have learned so far, we can actually determine if the grams of table salt in a particular food product, that we can actually derive how many grams of sodium that actually entitles to. Typically for the recommendations for the diets, I think it is 2,000 milligrams. I think 2 grams is the recommended daily intake of table salt. So again, that's why sometimes we just have to watch the salt. So there's some people that don't utilize it at all, but we're going to see how we accomplish that calculation. So the first thing that we're going to write is the amount given, that in here is 4.05 grams of NaCl. And then we have 3 conversion factors. In our conversion factor number 1, as you can see, we're going to utilize the molar mass of the compound to find the moles of the compound. So we are going to divide by the molar mass of the compound, okay? And locally, in a previous problem, we already determined what is the molar mass of NaCl. As you can see, is 58.442769. That's how many grams of NaCl are in 1 mole of NaCl. Then we're going to use our second conversion factor, which is based on the formula subscripts. We're going to relate the moles of NaCl to the moles of sodium. The relationship is 1-to-1 because in the chemical formula, NaCl, there's only 1 sodium, okay? Lastly, we're going to use the molar mass of sodium to finish the problem. So we're going to say 1 mole of sodium, and then we're going to put the molar mass of sodium. 22.989769 grams of sodium, okay, are in 1 mole of sodium. When it comes to the unit cancellation, grams of NaCl cancel with grams of NaCl, moles of NaCl with moles of NaCl, moles of sodium with moles of sodium. So to get this final answer, we're going to multiply 4.05 times 1 times 1 times 22.989769, everything divided by 58.442769. And since we're multiplying by 1, then we just keep that number. So how many grams of sodium are in 1 cup of cheddar cheese? When we round it to 3 sig figs, 1.59 grams of sodium. Okay. The reason why we don't round it to 1.60, even though 1.60 has 3 sig figs, is because the digit next to the 9 is a 3. So you're over rounding if you suggest that 1.60 is the final answer. Be careful with the rounding rules. Okay. So as you can see, 1 cup of cheddar cheese is very close to the daily intake, which is 2 grams of sodium per day. So maybe low sodium cheese. I don't know. This one has a lot of sodium. Let's do some practice problems where we are calculating the mass of an element given the mass of a compound. Let's do at least one of these. Okay, so in problem number 1, you're calculating how many grams of oxygen are in 25.0 grams of carbon dioxide. Okay, so I'll give you guys 2 minutes to do that. Yeah, sometimes we don't even realize eating a whole cup of cheese. But if you have like broccoli cheese soup, oh my God. Now I do it vegan, right? Just because I have my dairy allergy, but I don't even know how much cheese is in that, but that soup is delicious. Especially the one in Panera. Panera makes really good broccoli cheese soup. I miss it. I can't have it anymore. And their mac and cheese. That's my son's favorite. Panera mac and cheese. Which now that they sell it at Costco, he is so happy. So I'll give you guys 2 minutes to do problem 1. So remember, when you're given grams of compound and you're trying to find grams of element, the first thing that we're going to do is divide by the molar mass of that compound, okay? Then we're going to multiply the value of the subscript for the element that we're interested in. And then we're going to multiply by the molar mass of the element that we're interested in. So let's set up the equation for problem 1. We have 25.0 grams of CO2. As you can see, we're going to divide. That means that in the bottom of my fraction, I'm going to put the molar mass of CO2. So molar mass of CO2 is going to be 15.9994 times 2 plus carbon, which is 12.0107. So my molar mass is going to be 44.0095 grams of CO2 equal 1 mole of CO2. My next conversion, I'm going to multiply by the subscript of the element that I'm interested in. In this case, it's going to be oxygen. So there's 2 moles of oxygen in 1 mole of CO2. Lastly, we're going to use the molar mass of my atom. So 1 mole of oxygen, and on top is going to be 15.9994 grams of oxygen. When it comes to canceling, grams of CO2 cancel with grams of CO2, moles of CO2 with moles of CO2, moles of oxygen with moles of oxygen. So when we do this, 25.0 times 2 times 15.9994 divided by 44.0095. I got the same thing you got when we round it to 3 sig figs, because the value 25.0 has 3 sig figs, is 18.2 grams of oxygen in that many grams of CO2. Any questions on the calculation of finding grams of an element given grams of a compound? Great job for people that also put the answer in the chat. Excellent. So we're going to now move on from talking about math, and now we are going to talk about specifically the equations of chemical reactions, okay? So we learned previously that matter can undergo chemical change, and that chemical change can be given by a chemical reaction, okay? Remember that chemical change, we start with a substance that is going to be converted into one or more substances, and those brand new substances have different formulas and they have different properties, okay? Now, there's different things that are going to indicate that a chemical reaction has occurred. And as you can see, those include the change of color, because the new compound or molecule produced has a new color. The emission of light, again, because that new compound has the ability to emit light. The formation of a solid. What is the word that we use for formation of solid? No, when we have a chemical reaction and we form a solid, what is that called? I mentioned it to you guys before when we did chemical change. Somebody recalls that word? It starts with a P. Formation of a solid in a chemical reaction. Or precipitate. Okay. So if I have a chemical reaction and I form a solid, that is called a precipitate, because something is precipitating, it's precipitation. Then if the new molecule formed is a gas, then understand that that's where the bubbling comes from. Also, generating heat or absorbing heat is an indication that a chemical change has occurred. Now, how do we illustrate chemical changes? By doing a chemical equation, okay? And chemical equations have very specific symbols that are utilized, and you need to be able to understand them, okay? So, you need this table in exam 2. Because you need to understand the different symbols in a chemical equation, okay? So, understand that any molecule or element that is on the left of the arrow, that is called a reactant, okay? Those are the things that are going to start the reaction. Anything to the right of the arrow is called a product, okay? And you need one or more reactants, and you can get one or more products, okay? Whenever you have multiple of either reactants or products, we utilize the plus sign to separate them. The arrow indicates the direction of the reaction, meaning how these reactants are going to form product for that matter. If you apply heat to the reaction, as you can see in the symbols, okay, you're going to see that triangle. That's the delta symbol. That means that we are heating the reaction, okay? Another thing that can be incorporated into reactions is the state of matter of the components of the reactions. And you can see that we can put an S for solid, an L for liquid, a G for gas, and one that is brand new that we have never talked about is aqueous. Aqueous is going to be given to molecules. Most of the time it's going to be ionic compounds. Or other molecules that are in water. That is what aqueous means. And those symbols that you see, the little s, the little l, the G, or the AQ is going to be placed in the bottom right corner of the chemical formula for the components of the reaction, okay? Now, we need to understand that there are 5 different types of reactions that you guys need to be familiar with, okay? The 5 types of reactions that you guys need to be familiar with are the following. Starting with a combination reaction. How do I know that my reaction is a combination reaction? Well, you're going to have 2 or more reactants, but it's called a combination reaction because they form a single product. Now, we also have what is called a decomposition reaction, which you can see is the second bullet point. And in a decomposition reaction, we start with a single reactant and it's going to split into two or more products. Then we have the replacement reactions. And as you can see, we have either a single replacement or a double replacement reaction. In the case of a single replacement reaction, and as you can see here, the letters are just giving you, these are going to be the molecules. They're just letter symbols for the molecules. In a single replacement reaction, let's say that you have molecule A and you have compound B and C. The reason why it's called is a single replacement is because compound A is going to replace one of the portions of compound B and C, and that's why it's replacing B in the original compound. Then we have double replacement reactions, and in double replacement reactions, how we observe them is that typically these are going to be two ionic compounds that are aqueous. And they are going to, in water, split into ions. A is going to be a cation, B is an anion, C is a cation, D is an anion. And in a double replacement reaction, what they are going to do is that they are going to basically switch partners, okay? Now, A, which is a cation, will be paired with D because it is an anion. So in this switch up of partners, now we have a brand new compound, which is A and D coming together. And then we have the cation C with the anion B, and that's where CMB comes from. We have one more type of reaction, which is a combustion reaction, okay? In combustion reactions, understand that by definition, a combustion reaction is going to be any molecule that reacts with O2. That's what makes a combustion, okay? Now, in the example that we have here, which is CH4 reacting with O2, making CO2, water, and energy, this case is very specific, okay? Because combustion reaction, if your reactant has carbon, hydrogen, or carbon, hydrogen, and oxygen, when combining with O2, it will always form CO2, water, and energy, okay? So that is very specific. So there's a question in the chat. Is there a reaction that splits all elements and there is no combination of elements? I'm not understanding your question, Victoria. When we have reactions in chemistry, all the elements that are in the reactant are going to show up in the product. We're not going to have brand new elements show up. So I'm not sure.
No new elements, but just basically you're splitting old elements. So you have a reaction that occurs and it will split A from B, and that B or A will not recombine with anything else on the product side. So you're just left with a bunch of split up elements versus any kind of compounds.
You could, like, for example, if you take water, and water can undergo the process of electrolysis, which is a decomposition of it.
Yes,
And when it
yes.
does that, then you form just molecular hydrogen and just molecular oxygen.
Great,
So
thank
you
you.
don't need brand new compounds. They are just molecules. Excellent. So these notes about the types of reactions have been summarized in table 7.5. You can also see examples of combination reactions, decomposition reactions, single replacement reactions, double replacement reactions, and even combustions in this table. So for the exam, it is important that you guys know if you are given a particular reaction that you can visualize the reaction and say, okay, if I keep track of what's happening in the elements, I'm going to determine what type of reaction am I dealing with, okay? So, as you can see here, we have 8 of them because we only have a couple of minutes. Let's do at least the first 3. And when we come back next week, then we can continue and review this so we can proceed to the other topics in this chapter. Let's do the first 3. In number 1, if we observe closely what's happening at the atomic level, what's happening in terms of the atoms, we can see that we have HNO3 reacting with nickel. And then when we look at the product, now nickel is with the NO3, and then H is by itself. So it's kind of like nickel took the place of the hydrogen. What kind of reaction is this? Combination, decomposition, single replacement, double replacement, or combustion? So nickel took the place of hydrogen, and now hydrogen is by itself. Excellent. This is a single replacement reaction. Number 2, we have barium bicarbonate, okay, by itself, and we can see that that single compound made barium carbonate, water, CO2. So if we have one single compound splitting into many, what kind of reaction is this? Excellent. Decomposition. The reason why this is not a combustion, because I saw it in the chat, is because remember, in a combustion, O2 must be in the reactants. Here, we don't have O2 in the reactants. We have a single compound just splitting into many things, okay? So don't adjust your eyes to say like, oh, if I see H2O and CO2, that's combustion. That is not. Combustion is very specific. Let's look at number 3. I have molecular nitrogen with oxygen making N2O5. So I have 2 things making one product. Excellent. This is a combination reaction. But like somebody also put in the chat, this can also be a combustion reaction. Why is this a combustion reaction? Because we are reacting something with O2. Okay? So this is where I'm going to stop lecture for today. Thank you guys for coming.